So I want to drop you, the listener, directly into the cockpit. Like imagine you are the captain.
Right. Sitting in the left seat, hands on the controls.
Exactly. You are hurtling down this massive stretch of runway concrete. You are well past 100 knots, maybe doing, I don't know, 130, 140 miles per hour.
Which is incredibly fast when you remember you're strapped to thousands of gallons of highly volatile jet fuel.
Yeah, exactly. The center line is just, it's blurring into a solid white streak beneath you. And suddenly, an alarm begins to blare.
And not just a soft cautionary chime, we're talking about the master warning.
Right, the master warning. The screens in front of you are flashing red. Critical systems are failing in real time. And your immediate, deeply ingrained human instinct, the exact same self-preservation instinct you use every single day when, say, a deer runs out in front of your car, is to just slam on the brakes.
It's pure biology. We are wired to stop moving toward danger.
But, and this is the wild part, what if I told you that in this highly specific moment, attempting to stop is actually the most dangerous thing you could possibly do?
It completely short-circuits our natural wiring, doesn't it? I mean,
Yeah.
millions of years of evolutionary survival tactics scream that danger is ahead and we need to stop.
Right.
But physics and the terrifying mechanical reality of the aircraft in that split second, they dictate the exact opposite.
And that paradox, that is the mission of this deep dive today.
Yeah.
We are poring over a stack of highly specific, genuinely intense aviation flight manuals.
Very dense, very technical manuals. Yeah.
Very dense. And they detail this scenario known as an electric emergency configuration, or ELEC-EMER config. We're going to explore the mechanical, physical, and frankly the psychological reasons why taking a profoundly broken, malfunctioning airplane into the sky is, well, it's infinitely safer than trying to keep it on the ground.
Because survival in a high-speed aircraft isn't about applying terrestrial ground-based logic to a complex problem.
Ground-based logic just doesn't work at 140 miles an hour.
It doesn't. It's about deeply understanding the environment the machine is engineered to exist in. The sky is actually a haven.
The sky is a haven.
Exactly. The ground, specifically the rapidly disappearing concrete of a runway, is the primary threat.
So if the sky is a haven, we need to understand what makes the ground so lethal in this scenario. Let's look at the parameters from our sources.
Let's do it.
According to the manuals, we are looking at this massive electrical failure occurring precisely 20 knots below V1.
Which is a crucial detail.
Right. And for you listening, V1 is a critical aviation concept. It's the decision speed, the point of no return. Once you hit V1, you are committed to flying, even if an engine literally explodes.
You're taking that plane into the air.
Exactly.
Yeah.
But in our scenario today, we are below V1. Technically, theoretically, you still have the option to abort the takeoff and stop.
Theoretically, yes.
Yet, the manual describes this exact electrical failure as a, quote, severe downgrade to stopping and handling capabilities. So what actually dies the moment this electrical emergency triggers?
To understand the anatomy of this massive system downgrade, we have to look at the brain that manages how the aircraft interacts with the pavement.
Okay.
The primary victim here is the BSCU. That's the braking and steering control unit.
The braking and steering control unit. I mean, that sounds pretty fundamental to a vehicle rolling on the ground.
Oh, it is. It's the translator between the cockpit and the landing gear. And when this specific cascading electrical failure happens, the BSCU goes entirely dark.
Wow. Just completely offline.
Instantly. And when it dies, it takes 3 critical ground control systems with it.
Which are?
You lose normal braking, you lose anti-skid, and you lose nose wheel steering.
Wait, let's unpack that last one first. You lose nose wheel steering.
Completely.
I'm picturing the sheer sensory shock of that in the cockpit. Like, you are rocketing down a runway at over 100 knots.
Yeah.
You're constantly making these little micro adjustments to keep the nose of the plane perfectly aligned with the center line.
Right, using the tiller.
Yeah, the steering wheel, the tiller that the pilot uses. And then suddenly it just goes completely limp.
The mechanical connection is severed. The hydraulic actuators that turn the wheel lose their electronic commands. So the tiller in the pilot's hand becomes utterly useless.
That's terrifying.
Mm.
How do you even keep the plane on the runway then?
You are now entirely reliant on the aerodynamic rudder at the back of the tail to keep you straight.
Steering a 70-ton metal tube with a vertical fin in the wind instead of wheels on the ground?
It's wild, right?
That feels like a massive shift in how you handle the machine.
It is. And the physics of steering change in a fraction of a second. See, the rudder is incredibly sensitive at 130 knots because there is so much air rushing over it.
Right. Wind resistance.
Exactly. But if your speed drops, the rudder loses its effectiveness. So if you try to slow down, you're caught in this bizarre transition zone where you can't steer like a car, but you aren't fully flying yet either.
So you're basically drifting. And simultaneously, while you are trying to keep the plane from veering off into the grass, you lose normal braking and anti-skid.
Which is the real killer here.
I want to spend some time on anti-skid at those speeds because I don't think most people realize how fundamental it is. I mean, we think of anti-lock brakes in our cars as like a nice safety feature for a snowy road.
A luxury, almost.
Yeah, a luxury. But on an airliner, it's not an optional luxury at all.
No, anti-skid on a commercial airliner is the sole reason high-speed braking is physically possible.
Period.
Period. At over 100 knots, if you apply maximum hydraulic brake pressure to those wheels without anti-skid, the brake calipers will clamp down with such immense force that the wheels will instantly lock up.
So they just stop spinning entirely.
They stop spinning completely while the aircraft itself is still moving forward at over 150 miles per hour.
Oh my God. You are dragging stationary rubber across grooved concrete at racing speeds.
And the friction generated in that scenario is almost unfathomable. The tires don't just skid, they experience a catastrophic physical transformation.
A physical transformation, like what?
The heat generated by dragging stationary rubber across concrete at 150 miles per hour will literally melt the tire.
Wait, really? They turn into liquid?
They superheat. Think about the moisture that is naturally on the runway, or even just the chemical compounds in the rubber itself.
Okay.
The friction superheats that material in milliseconds, creating a layer of gas, steam, or molten rubber directly between the tire and the pavement. The technical term for this is reverted rubber hydroplaning.
Reverted rubber hydroplaning. I've never heard that before. So you aren't even touching the runway anymore.
Exactly. You are essentially sliding on a microscopic cushion of vaporized tire and steam.
That's insane.
It is. Your braking efficiency drops to near zero. And because the tires are locked and sliding on this vapor cushion, you lose all directional stability.
So you're out of control.
Completely. The plane will just drift with the crosswind or the natural slope of the runway, completely out of your hand.
That is a genuinely terrifying image. It's like driving on a highway at 80 miles an hour, and suddenly your power steering, your anti-lock brakes, and your normal brakes all just vanish at the exact same second.
That's a great analogy.
The sheer severity of this downgrade is shocking. But, and I'm playing devil's advocate here, an airliner of this size has to have backup systems, right? I mean, engineers don't just leave a multi-million-dollar aircraft and hundreds of passengers with absolutely nothing if one computer fails.
You'd think so, yeah.
There has to be a backup brake pedal.
Well, the manuals do detail an alternate braking system.
Okay, good.
But relying on it during a high-speed aborted takeoff introduces a very dangerous illusion of safety.
An illusion.
Yes, the alternate system exists, but its limitations are so extreme that attempting to use it at 130 knots is effectively a trap.
Okay, let's dig into those limitations because this is where the physics get incredibly tense.
Yeah.
The sources state that when the primary computers die, this alternate braking system relies on something called the yellow accumulator.
The yellow accumulator, yes.
What exactly is an accumulator and why is it painted as this desperate last resort?
An accumulator is a physical pressurized bottle hidden deep within the hydraulic architecture of the aircraft.
Like a tank.
Yeah, a spherical tank. Think of it as a mechanical battery, but instead of storing electricity, it stores kinetic potential.
Okay, how does that work?
Inside this heavy metal sphere, there is a diaphragm. On one side of the diaphragm is nitrogen gas, compressed to a massive pressure.
Right.
On the other side is hydraulic fluid.
Because you can't compress a liquid, but you can compress a gas.
Precisely. Under normal conditions, the aircraft's engine-driven hydraulic pumps push fluid into that sphere, compressing the nitrogen gas like a tightly coiled spring. But when this massive electrical emergency happens, the computers that normally manage your hydraulic pressure go offline. The valves close.
Oh, no.
Yeah. You are now entirely cut off from the endless supply of hydraulic pressure generated by the engines.
So you are left with whatever is currently trapped inside that single bottle.
You are relying entirely on the stored energy of that expanding nitrogen gas to push the hydraulic fluid down the lines and squeeze the brake calipers on the wheels.
And the manual specifies two terrifying limitations for this yellow accumulator. First, it is limited to a maximum brake pressure of 1,000 psi. Let's put 1,000 psi into context for the listener. How does that compare to what you actually need to stop an airplane?
Well, normal, healthy braking pressure when you slam on the brakes to abort a takeoff can exceed 2,500 to 3,000 psi, depending on the specific aircraft variant.
Wow. So 1,000 is nothing.
When you are restricted to the accumulator, you are working with less than half, maybe a third of your stopping power.
That's a massive reduction.
It is a feeble squeeze compared to the crushing grip required to halt that much kinetic energy.
So the brakes are weak. But the second limitation is even more alarming, I think.
Oh, definitely.
The manual says that the accumulator only holds enough fluid for about 7 full brake applications, just 7 pumps of the pedal.
The volume of the sphere is finite. Every time the pilot presses the brake pedals, they open a valve that lets some of that pressurized fluid travel to the brakes.
Right.
But when they release the pedal, that fluid returns to a low-pressure reservoir. It doesn't go back into the high-pressure accumulator.
Because the pumps are offline.
Exactly. So every single squeeze permanently depletes the nitrogen's stored energy.
Think about the immense psychological weight of that reality.
It's heavy.
You are hurtling toward the edge of the runway. The grass and the approach lights are approaching fast. And, intellectually, that you only have 7 squeezes of your toes before that bottle is completely empty.
And once it's empty, the pressure drops to 0.
And you have literally no braking power left at all.
None. The extreme mental discipline required to manage a finite number of brake pumps while hurtling down a runway is almost inhuman.
I can't even imagine.
Put yourself in the pilot's shoes. You press the brakes, you immediately feel the tires start to skid because remember, the anti-skid computer is dead.
So your instinct is to pump the brakes, just like you were taught in an old car on an icy road.
Right. But if a pilot gives into that instinct, if panic sets in and they rapidly pump the pedals trying to find traction that simply doesn't exist, they will bleed off that precious 1,000 psi in a matter of seconds.
Just burn right through it.
They will drain the accumulator before they've even slowed down by 20 knots. And then they will be left rolling at high speed with absolutely nothing to stop them.
But the wheel brakes are only part of the deceleration equation, right?
Thermally, yes.
Because usually when you see a plane land, the engines open up and roar really loudly to slow the plane down.
The thrust reversers.
Right, the thrust reversers. But the sources point out that in an ELEC-EMER config, the thrust reversers are completely unavailable. You have 0 engine braking.
The thrust reversers are heavily reliant on the electrical and computer architecture that has just failed.
So they just won't deploy.
The mechanical sleeves that slide back to redirect the jet exhaust forward simply won't actuate. You cannot use the massive power of your own engines to fight your forward momentum.
Okay, so let me summarize. No normal brakes, no anti-skid, a weak backup brake that runs out after 7 pumps, and no thrust reversers.
Then it gets worse.
It gets worse. The sources note that half the ground spoilers are inoperative.
Yeah.
Depending on the variant of the plane, spoilers 1, 2, and 5 are completely dead. Now, I want to explore these spoilers because their aerodynamic role seems to be vastly misunderstood by the general public.
It's a huge misconception.
When we look out the window upon landing and see those panels flip up on the top of the wing, the logical assumption is that they act like giant air brakes.
Like metal parachutes catching the wind, right?
Exactly, catching the wind to slow the plane down.
They do provide some aerodynamic drag, sure. And at 130 knots, pushing flat metal panels into the oncoming wind certainly creates resistance.
Right.
But their primary, absolute most crucial role is a concept called weight on wheels transfer.
Weight on wheels. Why does an airplane need to transfer its weight? Doesn't it already weigh like 70 tons?
It does. But an airplane wing is a miracle of physics designed to do one thing relentlessly: create lift.
Create lift.
As long as air is flowing over that curved surface, the wing is generating an upward force. Even when you are trying to stop, if you are moving at 120 or 30 knots down the runway, those wings are desperately trying to pull the entire aircraft into the sky.
Oh, wow. So aerodynamically speaking, the plane is actually incredibly light on its tires.
Exactly. The physical mass of the airplane hasn't changed, but the downward force exerted on the pavement is minimal.
Which means
Wheel brakes, regardless of whether they have 3,000 psi or 1,000 psi, only work if there is heavy friction between the tire and the concrete.
Oh, I see.
If the plane is generating lift, there is very little weight on the wheels. You can squeeze the brake calipers all you want, but the tires will just lightly skid across the surface because there's no downward force planting them into the grooves of the concrete.
The spoilers exist to kill that lift.
The moment the main landing gear touches down, or the moment a pilot aborts a takeoff, those ground spoilers pop up to instantly disrupt or spoil the smooth airflow over the top of the wing.
They destroy the aerodynamic lift.
When the lift vanishes, the entire 70-ton weight of the aircraft crashes down firmly onto the landing gear struts, driving the heavy rubber tires violently into the pavement.
And that massive friction is what allows the brakes to actually do their job.
Exactly.
But in our electric emergency configuration scenario, half of those spoiler panels failed to deploy.
Because the computers that command their hydraulic valves are dead.
Which means a significant portion of the wing is still doing its job.
It is still generating a massive amount of lift. The aircraft simply refuses to put its full weight onto the wheels.
Okay, let's assemble this horrifying mechanical puzzle.
Let's do it.
You are screaming down the runway. You attempt to stop.
Yeah.
Half your spoilers don't deploy, so your plane is still fighting to fly, making your tires incredibly light.
Right.
You have no anti-skid, so if you press the brakes too hard, those light tires will instantly lock, superheat, melt, and hydroplane on their own vapor.
Yes.
Because you are an expert pilot, terrified of locking the tires, you try to brake gently, but you are limited to a weak 1,000 psi anyway.
From the accumulator.
Right. And you know you only have 7 pumps of the pedal before you have no brakes at all. Oh, and your engines can't help you reverse.
It is the perfect, inescapable recipe for a high-speed runway excursion.
A runway excursion, meaning you're going off the pavement.
You are effectively driving a massive, volatile hovercraft with no steering wheel, no function, and a handbrake that's about to snap.
A hovercraft. That is such a good way to put it.
Attempting to stop under these physical conditions will mathematically guarantee that you slide off the end of the runway at a lethal speed.
So, if the mechanical reality dictates that the plane effectively cannot stop, we have to look at the rule book. We have to look at the doctrine governing the pilot's decision-making process in that split second.
The doctrine is very clear here.
Our sources are explicit about this so-called go-minded philosophy. They remind us that this emergency is happening 20 knots below V1, which places us well above 100 knots.
Yeah, high speed.
Why is that specific number, 100 knots, such a critical threshold in aviation?
The 100-knot mark is a major dividing line in the philosophy of takeoff safety.
How so?
The decision logic in the cockpit fundamentally shifts the moment the airspeed indicator crosses that number.
Okay.
Below 100 knots, you are in a low-speed regime. The kinetic energy state of the aircraft is relatively low.
Kinetic energy being mass times velocity squared.
Exactly. At 60 or 80 knots, the energy required to stop the plane is totally manageable.
Sure.
If a warning light comes on, if a tire blows, if a window pops open, or if a system glitches, the philosophy is universally stop.
Because it's easy.
The runway ahead of you is incredibly long, your brakes have plenty of time and grip to work, and the physical risk of aborting the takeoff is negligible. You just pull the throttles back, brake, and taxi back to the gate.
But the sources say that in the high-speed regime, nearing V1, the manuals explicitly dictate the captain must be go-minded.
Go-minded.
They define rejecting a takeoff here as a, quote, more serious matter that could lead to a hazardous situation.
Because above 100 knots, that kinetic energy equation balloons exponentially.
Because the velocity is squared.
Yes. It takes a monumental, violent amount of force to bring that much mass to a halt safely.
Right.
The brakes will glow red hot. The tires might literally deflate from thermal fuse plugs melting.
Oh, wow.
In the high-speed regime, you are taught to only reject a takeoff for catastrophic, unambiguous failures.
Like what?
A verified engine fire, a sudden and total loss of engine thrust, or a major structural failure like a wing breaking apart.
For almost everything else, the rule is to take the problem into the air.
The safest place to troubleshoot a complex problem is at 10,000 feet, not while hurtling toward a concrete wall at 150 miles per hour.
But wait, I'm looking at the manual notes here, and it points out a really fascinating contradiction.
Let's hear it.
It says that the activation of an ECAM alert, the electronic centralized aircraft monitor, you know, that main digital warning screen in the middle of the dashboard.
Right, the ECAM.
It says that an ECAM alert is technically one of the rare approved justifications for a high-speed rejected takeoff.
That's the standard operating procedure. Normally, if a master red warning flashes on the ECAM at 120 knots, accompanied by the continuous repetitive chime,
The loud alarm.
right, the manual unequivocally supports the captain's decision to slam on the brakes and abort. The system is designed to only throw a red warning at that speed if the failure is dire.
But this specific emergency, The ELIC-EMER config overrides that standard logic.
It does.
The sources state that even though the red lights are flashing and the alarm is screaming, attempting to stop with all these degraded systems, quote, would almost certainly result in a severe runway excursion.
You will go off the end of the runway, into
Yeah.
the grass, into the instrument landing antennas, into the airport perimeter fence.
Which is catastrophic.
This is where we see the monumental friction between human instinct, standard training, and specific emergency doctrine.
The friction, yeah.
Think about the pilot's cognitive load. They've been trained in simulators for years that a red ECAM warning at high speed is grounds to abort.
That's muscle memory.
The alarm is physically assaulting their ears. The instinct is to survive, to hit the brakes.
But the manual demands the captain coldly override that instinct.
They must recognize the specific, complex nature of the electrical failure in a fraction of a second, ignore the screaming alarms, and push the thrust levers forward.
How is that humanly possible? I mean, how does a person fight the biological urge to hit the brakes when every single flashing light is telling them the machine is dying?
It requires an extraordinary level of situational awareness, but more importantly, it requires pre-flight mental conditioning.
Pre-flight conditioning.
Pilots don't just figure this out on the fly. They brief this specific concept before every single takeoff.
Really? Every takeoff?
Before they even push back from the gate, they sit in the cockpit and literally speak the words out loud to each other.
The takeoff briefing.
Exactly. They will say, after 100 knots and prior to V1, we will only reject for engine failure, fire, or if the aircraft is unsafe to fly.
So they are actively pre-programming their brains.
They are building a mental firewall to be go-minded. The goal is to ensure that if an ambiguous or complex alarm like an electrical cascade flashes at 130 knots, their default physical action, their muscle memory, is to keep their hand firmly pushing forward on the throttles, not pulling back.
Because if stopping means a guaranteed high-speed runway excursion, which we just established it absolutely does, then the only alternative is to pull back on the stick and take off.
You have to fly.
But that leads to an incredibly terrifying thought in the core of our fourth section. What exactly are you flying into the air?
It's a great question.
We know the systems that broke on the ground. The brakes are gone, the steering is gone. What actually survives this electrical apocalypse?
This is where the aerospace engineering truly reveals its genius.
Okay, I'm listening.
We have to contrast the ruined ground-stopping capability with the miraculously intact flight capability.
The contrast.
The aircraft on the ground is an unsteerable, brakeless mess, but the aircraft in the sky is actually a highly capable flying machine.
First and foremost, according to the sources, you still have operating engines.
Yes.
Now, I have to stop here and ask a pretty basic mechanical question. If the entire electrical system of the plane suffers a severe downgrade, how do the jet turbines keep spinning? Doesn't a modern jet engine need massive computers and electrical sparks to burn fuel?
It's a brilliant question. But unlike a car engine that relies on a battery and an alternator to constantly fire spark plugs,
Right?
a jet engine relies on continuous combustion. Once the fire is lit inside the combustion chamber during engine start, it is self-sustaining as long as you feed it air and fuel.
Just air and fuel.
The sheer compression of the incoming air keeps the fire raging.
But what about the computers that control the fuel flow? Don't they need electricity?
Modern engines are controlled by a computer called FADC,
ADC.
Full Authority Digital Engine Control. And engineers knew better than to rely on the airplane's main electrical system to power the engine's brain.
Oh, that's smart.
So each engine has its own dedicated internal electrical generator driven directly by the spinning gearbox of the engine itself.
Oh, wow. So it's totally isolated.
Once the engine is running, it generates its own independent electricity to power its own computers and fuel pumps.
That is incredible engineering foresight.
Even if the entire fuselage goes completely dark, the engines will happily keep roaring, isolated and protected from the cascading failure.
So the engines are pushing you forward with maximum takeoff thrust. The plane wants to fly.
It wants to fly.
But what about the flight controls? The source notes that the computers revert to something called alternate law.
Alternate law, yes.
What does that actually mean for the pilot pulling back on the stick?
In a modern fly-by-wire aircraft like an Airbus, there are no steel cables connecting the pilot's joystick to the flaps on the wing.
Right, it's all digital.
The pilot sends an electrical signal to a bank of flight control computers, and those computers decide how much to move the hydraulic actuators on the wings. Normally, this operates in what's called normal law.
Which includes an entire envelope of software protections, right?
It's an invisible electronic cage. In normal law, the computer will not let the pilot bank the plane past 67 degrees.
Okay.
It won't let them pitch the nose too far up and stall the aircraft. It smooths out turbulence. It essentially protects the aircraft from extreme pilot inputs.
But these computers require data from sensors all over the plane to make these complex calculations.
And in an electric emergency configuration, some of those sensors and computer buses lose power.
Oh, I see.
When the system detects that it no longer has redundant, perfect data, it automatically downgrades to alternate law.
The training wheels come off.
Exactly. Many of those invisible safety buffers are stripped away. The computer essentially says, I don't have enough data to protect you from stalling, so I am handing direct control back to you.
So the pilot is flying raw.
The pilot is now flying a much more raw, unfiltered connection to the flight control surfaces. It might feel a bit more sensitive or a bit heavier, and the pilot has to manually ensure they don't exceed the aerodynamic limits of the aircraft.
But, and this is the critical point to our whole premise, the plane is completely capable of safe flight.
Right.
The wings still generate lift, the tail still provides stability, the ailerons still respond to the stick.
It flies like a conventional airplane. It just requires the pilot to actively fly it rather than managing a computer.
Okay, the engines work, the wings work, but let's talk about what the pilots can actually see inside the cockpit.
This is where it gets really stark.
Because the sources describe a profound asymmetry in the cockpit during this emergency. It states that the essential navigation and communication instruments remain for the pilot flying.
Specifically, the captain.
Right, sitting in the left seat gets to keep PFD-1. What does the primary flight display actually show them?
The PFD is their window to survival.
Okay.
It provides the artificial horizon so they know if they are pitched up or banked. It provides the speed take so they know exactly how fast they are flying.
Vital data?
And it provides the altimeter so they know their height above the ground. It is the raw data required to keep the plane in the sky.
They also keep ND1, the navigation display, which shows their compass heading and route. They keep the engine warning display, the EWD, which tells them that those self-sustaining engines are still producing thrust.
Yes.
And they keep VHF-1, a single radio to talk to air traffic control.
That is a highly curated, deeply intentional list of surviving instruments.
But here's the jaw-dropping part of the source material. The first officers display units like the screens on the right side of the cockpit.
They're entirely lost.
They go completely dark, just blank glass.
Blank glass.
The first officer is suddenly staring at a dead dashboard while the plane is screaming off the runway.
Yes. They lose their primary flight display, their navigation display. They are effectively blind to the aircraft's instrument state.
It's like when your computer encounters a fatal error and completely crashes, but then it reboots into safe mode.
That's a perfect way to describe it.
It strips away the high-res graphics, all the background apps, the dual monitor support, and just gives you the absolute bare minimum, ugly, low-resolution interface required to save your files and keep the motherboard from melting.
What is genuinely fascinating here is the human element behind the engineering.
How so?
Years ago, electrical engineers sat in a windowless room and ruthlessly prioritized critical system losses.
Oh, wow.
They looked at a theoretical scenario where an aircraft loses almost all of its electrical generation capability, perhaps a massive short circuit or the loss of all main generators.
And they had to make life or death choices about where to route the last remaining drops of battery and emergency generator power.
They played God with the electrical buses.
That's wild.
They engaged in what's called load shedding. They purposefully designed the system to instantly sever power to anything that wasn't absolutely critical for immediate survival.
So they accepted the total loss of ground control.
Yes.
They accepted the loss of the anti-skid brakes.
Yes.
They accepted that the first officer would lose all their screens.
They sacrificed all of that peripheral capability specifically to ensure that the captain's core flight instruments and the radio remained perfectly uninterruptedly intact.
They engineered the aircraft to force the pilot's hand.
Exactly.
By starving the ground systems and feeding the flight systems, they made the airplane terrible at stopping, but perfect for getting off the ground.
The machine itself is telling you the ground is no longer your friend. Take me into the sky.
Taking these two realities, a crippled, unsteerable, brakeless ground vehicle versus a degraded but entirely capable flying machine, how does aviation philosophy summarize this ultimate choice?
It's all about the airborne recovery.
Right, that brings us to our final discussion, the airborne recovery. Let's talk about time, space, and the bigger picture.
The manuals conclude, without a shadow of ambiguity, that continuing the takeoff is the safest and highly recommended course of action.
The only logical choice.
This completely aligns with the overarching industry-wide philosophy regarding other high-speed anomalies, like massive tire blowout.
Right. The sources explicitly mention that. If a tire explodes at 130 knots, you don't slam on the brakes and risk the shrapnel tearing into the fuel tanks or the gear collapsing.
No, you don't.
You get safely airborne, handle the ECAM procedures in the sky, and return to land on a massive, prepared runway.
Let's contrast the risk of stopping versus the airborne recovery. Let's look deeply at the variables of time and space.
Okay, time and space.
On the ground, during a high-speed abort 20 knots below V1, you have 0 time and 0 space.
None.
You have perhaps 10, maybe 12 seconds before you reach the absolute end of the concrete. You are traveling at hundreds of feet per second.
The runway length is just rapidly, violently fading beneath.
You can literally see the perimeter fence rushing at the windshield.
And your brakes are crippled.
Your spoilers aren't helping. The physical environment is chaotic, it's loud, the airframe might be vibrating from the degraded system.
And the cognitive load.
The cognitive load on the pilot is at its absolute suffocating maximum, and they have literally no time to process the complex alarms.
It is pure reactive panic management. You are just fighting physics and losing.
But if you override that panic,
Yeah.
if you pull back on the stick and take that broken airplane into the sky, everything changes.
How so?
You trade runway concrete for altitude. You buy yourself the two most precious commodities in any emergency time and space.
It really is a brilliant logic when you step back from the immediate visceral terror of the alarms.
Is.
You are essentially hitting the pause button on the emergency. You are taking a crisis that is guaranteed to kill you in 10 seconds on the ground, and you are lifting it into a safe, endless environment, the sky, where you can deal with it on your own terms.
The moment you are airborne and climbing away from the ground, the immediate threat of a collision vanishes.
You can actually breathe.
You can breathe. The captain, utilizing those protected surviving screens, flies the aircraft manually in alternate law and climbs to a safe altitude, say 10,000 feet.
Right.
They establish a holding pattern, just flying huge, lazy circles in the sky. Now, the dynamic in the cockpit shifts from panic to methodical management.
But what does the first officer do since their screens are dead?
The first officer pulls out the QRH.
The QRH.
The Quick Reference Handbook. It's a physical paper binder or sometimes a dedicated tablet that survives the power loss.
Okay.
Even without their flight displays, they can slowly, methodically read through the specific checklists for an ELIC EMER config.
So they become the troubleshooter.
Exactly. They can troubleshoot, they can attempt to reset breakers or restore power using backup generators.
And they use that one surviving VHF radio to declare a mayday with air traffic control and ask for a holding block.
And most importantly, they can actually do the math on the brakes.
That's the crucial part.
Yes.
Instead of guessing how much stopping distance they need while actively skidding sideways off a wet runway.
They sit calmly at 10,000 feet, pull out the landing performance charts, and do the cold, hard calculations.
Run the numbers.
They can say, okay, we have no anti-skid, we have no thrust reversers, half our spoilers are dead, and we only have 1,000 psi of braking pressure from the accumulator. Based on our current weight and the weather on the ground, we mathematically require exactly 11,500 feet of dry pavement to stop this aircraft safely.
And if the airport they just took off from only has an 8,000-foot runway?
Then they simply don't land there.
Wow.
They use their perfectly capable flying machine to divert. They fly to a military Air Force base with a 13,000-foot runway, or a major international hub with massive wide runways.
They find the space they need.
They calculate the perfect approach speed. They prepare the cabin crew for an emergency evacuation on the ground.
And the emergency services.
They have the crash fire rescue trucks pre-positioned at the exact taxiway intersection where they calculate the plane will finally, slowly roll to a stop.
But they completely solve the problem before they ever touch the ground.
There is a profound life lesson embedded in this dry, technical flight manual.
What's that?
Sometimes pushing through a crisis, maintaining your forward momentum, and elevating yourself out of the immediate danger zone gives you the perspective and the space to actually solve the problem.
That's so true.
Instantly retreating, giving into the primal instinct to just hit the brakes and stop, seals your doom because you simply run out of runway.
That is an incredibly powerful way to look at it. Let's summarize the journey we've taken today through these manuals.
Let's recap.
You are in the cockpit. The alarms blare. You have suffered a massive electric emergency configuration at high speed. Instantly, your ground vehicle identity dies.
It's gone.
You lose your normal brakes, your nose wheel steering, your anti-skid, your thrust reversers, and half your ground spoilers.
The ground systems are dead.
Every instinct in your human body, every cell, screams at you to abort and stop.
It's terrifying.
But by understanding the strict, terrifying limitations of your alternate accumulator braking versus the intact, protected, highly capable survival of your flight instruments and jet engines, you realize that the sky isn't the danger.
The sky is your safest refuge.
It is an elegant, if terrifying, engineering solution to an impossible physics problem.
It really is.
But as we look at this deeply human interaction between a pilot's biological instinct and rigid manual doctrine, it leaves me with a final, provocative thought to mull over.
Oh.
We are rapidly moving toward a future where aviation relies more and more on artificial intelligence and fully autonomous flight systems.
The era of the computer flying the plane from the gate through the flight to the next gate.
Exactly. And the fascinating question becomes, how will we program a neural network to experience a massive cascading system failure?
That's a great question.
How will a computer react when every single digital alarm and sensor is screaming that the aircraft's architecture is dying?
Will it be able to handle it?
Will it coldly, mathematically calculate that continuing to accelerate toward the rapidly approaching end of a concrete runway is the only logical way to survive?
That's entirely possible.
Will machines, entirely unburdened by human fear and self-preservation instincts, actually be better at being go-minded than we are?
Wow. That is a wild thought to leave on. Will a computer be better at ignoring the instinct to hit the brakes simply because it doesn't have an instinct to begin with?
It just runs the physics calculation and pushes the throttles forward?
Right. It just executes the math.
Well, I hope you found this deep dive into the ELA Keymer config as fascinating and beautifully counterintuitive as we did.
It's been a great dive.
Keep seeking out those moments of discovery in your own deep dives into learning, and remember that sometimes, when everything goes wrong, the safest thing to do is just keep pushing forward.
And the next time you find yourself wanting to immediately slam on the brakes in a crisis, just remember,
Yeah.
sometimes stopping is the only thing that will guarantee a crash. You have to take the problem into the air.